0.5,
1/2, good.
and then 0.5e.
What, how about, give me the diagonal first.
Oh,
Middle 0?
0.5e to the,
What, this is 0.5?
yes,
Alright, so 0.5 e to the j,
90.
90 degrees. Go ahead.
And then 0.5, oh, there's only two.
Oh,
It's
2 by 2.
Yeah.
Go ahead. This one?
0.5e to the j 45.
And here?
And then 0.5e to the j 45.
Alright, now, he's gonna ask a few questions. Is it lossless? Probably one. And is it reciprocal? I'm guessing. Alright, so, if you wanna see if something is a reciprocal matrix, now I'm not gonna test you on this, but there's actually two things. For reciprocal, well, we'll do lossless first. So lossless is if you take the actual, and the way he does it, he's going to have the conjugate of the actual matrix, I believe, times the transpose equal to the unitary, and that's to see if it's lossless. You can check on that. And again, we're going to do it. We'll do it. But I want to tell you what this is, because I don't really do this. To me, I have my own ways. All right, so this is on page 563. It's transpose times conjugate is equal to unitary. So I have transpose. I have the conjugate first. It doesn't really matter. Transpose times conjugate of the matrix is unitary matrix. Now, what is a unitary matrix? It's just where the diagonals have 1 and everything else has 0s. Y'all follow me? That's all it is. So if we do this, first of all, what is the transpose of this matrix? Right here. What does the transpose do? The diagonals stay the same and these flip, right? Y'all remember that? Alright, so here you would have, and I'm just going to put down 0.5, and if you flip those, it doesn't matter, this is 0.5 e to the j 45, this is 0.5 e to the j 45, and this is really 0.5 e to the j 90 degrees. So that's going to be the transpose. What's the conjugate of the matrix? What does conjugation mean? If I have one at an angle of 30 degrees, what's the conjugate of that? One at an angle of minus 30. Do y'all follow me? Wherever the angle is, if it's positive, it becomes negative. If it's negative, it becomes positive for a polar number. So if we take this and we go ahead and do the conjugate of it, it's going to be, I'll put 0.5 here. This becomes 0.5 e to the minus j 45. This is going to be 0.5 e to the minus j 45, and this is going to be e to the minus j 90. Y'all follow me, class? I'm just putting it down. I'm going to see if when I multiply that out, if I get the unitary, if I just get ones in the diagonal. So let's see if we do. We come here. Remember, first term here, it's row column, right? Y'all remember doing this back in when you're algebra? So row, I have 1/2 times 1/2 is 0.25, right? And then what do I have next? I have 0.5 times 0.5 is 0.25, and is that right? It's this times this, so I have 0.5 squared plus, and this is going to be 0.5 squared, and that's, so it's 0.5, isn't it? Class, y'all follow? Well, that right there tells me I don't need to go any further if that's correct. If that first term is 0.5, then it's not 1. Y'all follow me? So, in fact, it isn't going to be a lossless system. Does he have that as the answer? It's not, because if you got a 1 there, I'd keep going. But I did. I got a 0.5. I know if that's the case, if it's not either 0 or 1, I don't need to go any further. It's not lossless. So now the next part is if it's reciprocal, right? Does he ask that? So for reciprocal, the way he does it, he's going to use the actual if the transpose is equal to the actual matrix. That's the only, this is on page 562. You can usually just look at them. So, to see if it's reciprocal, and we already answered that question, isn't this the transpose? Isn't it identical to this? So it is a reciprocal network. Now, I would not ask that per se. I may give you a circuit and ask if it's lossless. Y'all follow me? And what's the easiest way to tell? If there's a resistor, it's not lossless, right? But if it's just inductors and capacitors, then it is. Y'all hear me on that one? That's the way I do it, and that's the way in the real world we would. Now, the exception is if you're doing measurements over a wide, where you can't actually look at the internals of the circuitry, and there could be losses you didn't expect, then when they do measurements, they will do this right here, where they'll take the transpose times the conjugate to see if, in fact, you get primarily just diagonals with ones. But you're never going to get exactly one. There'll always be like 0.98, something like that. They want to see how close it is. And that's just the reality of these situations. What else? Is there any other questions for that one?
The return loss.
On this one? Well, they have to give me a circuit.
So determine the return loss looking into port 1. Port 2 is terminated
Okay.
in a shorted Z0 stub.
All right, so these are the S parameters, so now I'm going to do this. And return loss means I got to find the reflection coefficient. That's the bottom line. So here, we're going to have this. Here's my matrix, or here's my S. And this is port 1. Here's port 2. And it's terminated into what?
A shorted Z0 stub of electrical in 45 degrees.
Okay, this is a good one. This is actually a good one. So now they're going to say this. They have something that has a phase difference of 45 degrees. And they short it, okay? Now, just keep in mind that's port 2, and I want to go through this with you. This is a good one. How many took a look at that one? One. Well, better than none? Okay. I want you to be careful on this one, because I will ask something like this. This is port 1. We know we have V1 plus going in. We have V1 minus coming out. Here, this is port 2. We have V2 minus and V2 plus, correct? I'm just showing you on the ports what they mean. When I look at the equation, V1 minus is equal to S11, V1 plus S12, V2 plus, V2 minus is equal to S21, V1 plus S22, V2 plus, correct? I'm just putting them down so you can see. Now I'm not going to even write the values down at S yet, but I want to go through something. When you look at this, now just be careful now. V2 minus coming out keeps going, right? And it hits a short circuit, and then it reflects back, right? When I look at a short circuit, what is the reflection coefficient?
-1.
-1, isn't it, class? So I want you to think about this. I'm going to get V2 plus in terms of V2 minus. Here's V2 minus, whatever it is. Now, it goes through 45 degrees of phase change this way, right? Then 45 back, and it also has an additional -1. Y'all follow me? So I'm going to go ahead and say this is going to be -1 times e to the minus j, and that's going to be 90 degrees. Y'all follow me how I got the phase difference? Whatever it is here, when it hits here, it's e to the minus j 45 degrees. Y'all follow me on that? Then from here to here, it's e to the minus j 45, or a total of e to the minus j 90, right? I put the -1 in here because it's a short. Correct, everyone? Now, when I take a look at this, what do I get? Well, I have minus V2 minus times e to the minus j 90 degrees. What's another way to write that? E to the minus j 90 is what? Well, e to the j 90 is plus j. E to the minus j 90 is minus j. Do you all agree with that? Think about it. E to the j 90 degrees, the same thing as e to the j pi over 2 radians is just j, isn't it? Please make sure you see this. If I have e to the minus j90, that's e to the minus j pi over 2, that's minus j. Correct, class? Please make sure you see this. I know it seems trivial, but it's not. So I come down here, and I have a minus 1 here, and then I have e to the minus j90. That's really just minus j, isn't it? Times the minus is plus j. Or I can say this, right here, is just j. I don't have to put 90 down. I like j better. It's easier. Does that make sense? Everybody see this? Okay. So now I have V2 plus in terms of V2 minus. Okay. And that's really, at that point, he wants return loss, right? Return loss is going to be what? V1 minus over V1 plus. That is the reflection coefficient of port 1. We need that to get the return loss. Do you agree with that? All right, now, to get that, what I'm going to do is take a look at this, and I'm going to get V2 plus out of here, but I'm going to first take V2 minus, and if you look at V2 minus, it's really V2 plus divided by J, or minus J V2 plus. Do you all follow me on that? Make sure you do. You all follow me? So when I do that, I'm simply going to put this V2 minus is really going to be minus J V2 plus. All right? You all understand why? Because I equated this to that, and I've got V2 minus over there, so that's equal to minus J V2 plus. Agreed? Want to make sure. All right, now if that's the case, now I come over here, and I'm just going to rearrange this. And I just take a look at this. I want V2 plus by itself. So if I take this term over here, I have V2 plus, and it's times minus J, and then minus S22, right, is equal to S21 V1 plus. Did you all follow me? What I've done? Now I'm going to get V2 plus by itself. So V2 plus is equal to S21 V1 plus divided by this. Well, I can put it as probably, I'll just put the minus sign up here, and I'll have S22 plus J. Now again, I'm doing it in terms of J. You could put either J90 if you like. Agreed, everyone? Now I'm going to take that and I'm going to stick it in that equation, that first equation. And that one I'm going to write over here. So I have V1 minus is equal to S11 V1 plus S12 V2 plus. Here's V2 plus. So it's really going to be minus, right? And then I have S21. Then I have V1 plus, and it's over S22 plus J. Y'all follow me? I didn't even put in the values yet. I'm manipulating this to the point where I can determine that just by the next step. So now when I take V1 minus over V1 plus, I just get rid of this, and I get rid of this. And now I have the reflection coefficient at port 1. You all agree? I didn't put any values in, but I'm making sure you see it. Everybody see that? That's the reflection coefficient. S11 minus this. By the way, it's the only problem I believe. Or another problem. Actually, he does an example with this in it. So now we put the values in. So this is S11. Well, S11 over there is 1/2 or 0.5. And then it's minus S12 times S21. So when I multiply these two together, I get 0.25 e to the J90, don't I, class? This is S21, this is S12. So it's 0.25 e to the J90 degrees. I'm going to leave it like that for now. And it's divided by S22 plus J. This is S22. I want you to just watch this for a second. You all see that's S22? Right here? Now look, that's really what? 0.5 e to the J90 is simply J, right? I take that plus J. So I have, 1.5 J on the bottom. Right there, don't I, class? If I've done my math right. You all agree with this? Alright, now what happens? Well, what is each of the J90? We just talked about this. J, isn't it, class? Right? So I can replace this by J. Y'all see the J's go away, correct? So what do I get as my answer? I have 0.5, right? And it's minus 0.25 a quarter over 1.5. So, 1 quarter divided by 3 halves, right? So that's 1/6, right? So it's 1/2 minus 1/6. Can you give me the number on that? Let's see if that we get, I want this number first before we do a dB. Anybody? Y'all agree with what I'm doing, the way I'm doing it? Okay, what did you get? Say again? 1/3. This is 1/3? Okay. 1/3. Now, if we want, so this is 1/3. That's kind of interesting. Now, when we want the return loss, what is that? Minus 20 times the log of the magnitude of that which is 1/3. And what's that? dB. The minus 20 is there because even though it is a loss, that minus 20 will make a positive value, not a negative value. That's the reason. We know it's going to be a loss. Anybody? No, I want to see if it's right.
9.54 dB.
9.54? Anybody else? Is that the book's answer?
Yeah.
9.54, that's dB. Alright, now I'm going to tell you one thing. I didn't have time last time. But you'll notice the key to solving this last part was relating V1 plus to V1 minus. Right? Now I have a question for you. I'm going to change this. I want to see how you react. What if I said, instead of that, leave it to 45 degrees, but instead of a short, it's an open. Now, what is the relationship between V1 or V2 plus and V1 minus? Always take a look at this. Coming out is V1 minus, right? It goes through a phase change of 45 to there, correct? Now what's the reflection coefficient going into an open circuit? 1, isn't it? Reflection coefficient is the impedance you're going into. That's infinite if it's an open circuit, right? Minus the impedance you came from, which is Z0, over the impedance you came from, which is Z0, plus the impedance you're going into, which is infinite. So it's really infinity over 1, if you the limit that. So therefore, comes out, hits here, multiplied by 1, comes back, it's just what? E to the what? Minus J 90 degrees times V1 minus, isn't it? Or V2 minus. Y'all follow me? And then you would use this relationship to get this equation in terms of just V1 plus. Y'all follow me? I mean, you would use V2 plus. Basically, you would take this down here, all right? And then you would get everything in terms of V2 plus and put it there. But instead of a minus, that would be a plus, I believe. You follow me on that? How many understand that? Now, there's one last thing I could do, and I want you to think about this. Remember, they want the return loss, right? What if I did this? I'll put this into a resistance where this R is equal to Z0. Just think about it for a second. Now, what is the relationship between V1 minus and V2 plus and V2 minus? Well, if this has got a characteristic impedance of Z0, what is the reflection coefficient? 0. If it's 0, how much comes back? 0 means V2 plus is 0. Means you go right here, erase that in your reflection, because that's the match condition. Your reflection coefficient is just S11. You all see that? These are, some of, this is a little bit, there's subtleties in here, sometimes it'll drive you nuts. Wentworth has a way of connecting port 2 to port 3 through 90-degree segment, and then port 1 to port 2 through a 45 and asking for something like reflection coefficient, something like that. It'll drive you batty unless you get this straight in your head. Then you can do it, right? And it's always getting a relationship for the in-port voltage to the, I should say the plus to the minus voltage at that port. That's real important. Another one, that's a good one. That's a real good one. I'm serious about that. I had some in mind, but that's an excellent one because we didn't talk about that. I don't think we did anything like that, did we? That was pretty good. I just said what else is that for? Go ahead, Joe, what's that? You have one?
Not really, I didn't have any other problems with.
Some of these problems will cause you to think, really, think in a hard way.
Maybe 2.6 would be good.
What's that?
In a 50 ohm system.
One second, I'll try to get some of this up. Go ahead.
In a 50 ohm system, a 2-port network consists
What
of
problem is this?
10.26.
10.26, go ahead now. 2 ports?
Z naught's gonna be 50. And then it says the 2-port network consists of a 25 ohm resistor in series followed by 50 in shunt. Calculate the return.
So here's what they got. A 25, right? And then they got a shunt 50? Okay.
And then port 2 is terminated in a 100 ohm resistor.
The termination right at this port.
Yeah, it says calculate the return loss looking at port 1 if port 2 is terminated in 100.
Alright, let me take a look at this problem, just for a second.
I don't see the link.
In a 50 ohm system, a 2-port network consists of a series 25 and a shunt 50. It's in 1014, whatever that is. Calculate the return loss looking at port 1 if port 2 is terminated into a 100 ohm resistor. That's right at the port. Now, this is a little odd, right? Because first, if we look at this by itself, we can get S parameters, right? Then he says he's terminating the second port into 100 ohms. Isn't that right? All right, now, here's where it gets a little sketchy. If there's any link here that can make this an actual transmission line, where you have a distance and it's 100 ohm, where this is more than a tenth of a wavelength round trip, that's a much different problem than putting 100 ohm right off this port. Right? Now, if that 100 ohms hanging right off that port, you see it effectively makes this look like 100 in parallel with 50. How many see that? It does, which means that's just 33.333 ohms, I think, if you take a look at it, right? All right, so if that's 33.33 ohms, here's what this circuit effectively looks like. For port 1, it's 25 ohms, then it's 33.33 ohms, and now, when we want the return loss here, where this is going to be 50 ohms, and we want the reflection coefficient at that port. Now that reflection coefficient becomes very easy to get because it's the sum of those two, 25 and 33.33. That's the input impedance. So when you take a look at this, the reflection coefficient of port 1 would be equal to the impedance you're going into, which is going to be what? That's 58.333 minus the impedance you came from, which is 50, over the sum of the two, which is going to be 108.333. So tell me what that is. But you all see what I'm doing here? Now that's one interpretation, because he didn't give a length. He gave me that thing was more than a tenth of a wave, or a total round trip is more than Kent, then I'd have to include the effects of that transmission line, phase change, but you didn't give me that. So what do you get for this?
.076, got 58.3.
Yeah, well, it's the sum of 25 and 33.33.
I got .077.
Okay. Right. And he's asking for the return loss, isn't that right? Okay. Yeah, the return loss. So the return loss is going to be what? In the port 1, that's going to be minus 20 times the log, right? Of the magnitude of 0.077. Can you tell me what that is? We'll see if it's right. Is this making sense to what I'm doing this class? You understand? Okay. If you're not, ask a question. And if you don't know what to ask, let me know. I'll try to help you figure out what you don't understand. What'd you get?
22.3.
22.3? Can everybody take a look at the answer now? It's 22.3? I don't like that one because you really don't have a second port. The only thing you have is 2 parallel resistors. Because if it's snug up against that, there is no effective second port link involved. Okay, that's the problem with that one. We should do at least one more. But does that answer the question? Go ahead, Seth.
One of the assignments problem 10.34.
Okay, hold on. 10.34?
It references the previous problem though, which you didn't assign.
References what?
It references the previous problem 10.33, which wasn't assigned though.
Oh, go ahead.
But 3.3 starts. It says,
10.33, go ahead.
a circulator reference to a 50 ohm impedance.
Hold on for 1 second. So we got a circulator. Right? Go ahead.
And then it gives the matrix. It might just be easy.
Where's it? This one? Okay, all right, if that's the matrix, what is he asking?
In 3.4 it says calculate the insertion loss in VSWR for the previous problem if the isolated port is terminated in a short.
Okay, now I'm gonna put this up here so you can appreciate everything. This is an interesting problem, but this will cause you first see it, you might get shocked. It's like I don't know where to begin. You actually do. So for this one, for the S parameters, he has S here equal to, and it's going to be 1/2, or he actually uses 0.5, and then he has 1/2. The diagonals, I think, are all 1/2 of this one, 1/2. Then he has 3/4 e to the J60, and then down here he has 0.05 e to the J60. Then he has 0.75, and it's e to the J60. This is 0.05 e to the J60. This is this one is 0.05 e to the J60. And this is 0.75 e to the J60. And I need this matrix. Let me move that 1/2 over to do this problem. Okay, that's the S parameter matrix. And this is for, I'll call this for 1, 2, 3. Now, tell me about what was terminated. This is a good problem.
It said calculate the isolated port was terminated in a short circuit.
Let me explain something. Usually, if you have any, you could have 3-port, 4-port, whatever. An isolated port is usually the last port, which would be port 3 here. Just understand that's standard. And it's short, is it?
It's short, yes.
So here, he's gonna put a short here. Now what that means is whatever V3 minus is, or whatever V3 minus is, V3 plus is minus that. Y'all follow me? If you got direct short and no length of line, there is no phase difference other than the minus sign. Follow me on that part? So that means if that's port 3, I can say V3 plus is equal to minus V3 minus. Y'all follow me? Now what else does he say? Is this port 2 matched or not? I hope so.
He wants the insertion loss and visual.
Okay, but he's got to assume it's matched or else. Okay, so they want the insertion loss. So if that's terminated in short, he's assuming this is matched and that this is coming from the matched condition. So when you take a look at this, I mean, this is, I didn't make this puzzle, he did. It's just one of those things that when you look at this, V1 minus is going to be S11 V1 plus S12 V2 plus S13 V3 plus as such. And when we want, and he wants, he doesn't want return loss, just insertion loss? Okay. Then we have V2 minus is equal to S21 V1 plus S22 V2 plus S23 V3 plus, and then V3 minus is equal to S31 V1 plus S32 V2 plus S33 V3 plus. Here's what I'm doing what I'm doing. I'm going to work from here and get it down to something that's manageable. What I really want, if I want insertion loss, I want V2 minus over V1 plus. Right, that's what I'm after. That's what I'd like. Normally, that's just S21. Right? But the problem is, we've got a short circuit on port 3 there to worry about. So when we look at this, I know V3 plus is equal to minus V3 minus. I start there. You all with me? I come over here, and that means V3 minus is minus V3 plus. So on this equation, I'm going to change this to minus V3 plus. You all follow me? You'll see why in a second. So this is going to be minus V3 plus. And now what I'm going to do is get everything in terms of V3 plus. I'm going to pull out V3 plus, and then I'm going to modify this thing, because I want that one. So if I take a look at this over here, when I do it, I get, I have V3 plus, and then I have minus 1 and minus S33 there. Is equal to S31 V1 plus and S32 V2 plus. Now the only thing I'm doing is I'm just rearranging this so I have V3 plus over here. Then I can see that V3 plus is equal to S31 V1 plus S32 V2 plus over And I can put this whole thing as a minus one plus S33. Y'all follow me? I'm just rearranging. I'm gonna do something here. I'm gonna try to get this into a little bit easier form to work with. So if I look at this, one plus S33, well, S33 is 1/2, isn't it? So that's really 1.5. Everybody buy this? So I'm just gonna make this 1.5 down here. Now, when I look at this, I have S31, which is that thing. Let me see if I can get this down. Alright, so I'm going to take this right here and plug it into this equation next. And when I do it, I'm going to have V2 minus, that's what I'm after. It's going to be equal to S21, V1 plus S22, V2 plus S23, V3 plus, which is that, which is minus, making a minus here, minus S21, V1 plus S22, or I mean S32, I'm sorry, that's S31, S31 plus S32, V2 plus here, divided by 1.5. Now I have V2 plus, and what I really want is V2 plus, V2 minus over V1 plus. Then I get that V2 plus thing there. Does that cancel in this thing or not? V2 minus is equal to S21, V1 plus. What happens if we put the values in actually? S21. I'm just looking to see if this thing's going to cancel, if I have to really mess with it. S31. S23. Oh boy. I don't have a calculator in front of me, but I think there's going to be some cancellation here. I think all of the V2 plus goes away, I think, in this one. I can't see it though. I'm looking at that. S23 times S31, here's what I'm doing. I'm looking here what happens. And 23 times 31. 23 is right there. The 31 is right here, so it's really 0.05 squared times e to the j 120 degrees. We'll just see what happens here. And then I'm not going to spend a whole lot more time on this one, but V1 plus S22 V2 plus. Then this is going to be minus, this is 2/3 there, 0.05 squared e to the j 120 degrees, V1 plus S32 oh boy, it's going to be e to the minus j 1, well no, that's just going to be 0.75 times 0.05. times V2 plus, let's see here, that's 2/3. That's 3/4. It's gonna be minus, what's that, 2/2? I don't see that cancel. When it comes down to this point, I think, did you look at his solutions? Does he do this and then, sum up a bunch of stuff to get just V2 minus over V1 plus as a sum? Because this should go to that, but I think there's some cancellation right here that I don't easily see. Oh, V2 plus is 0, never mind. It's 0 because it's matched. This is assumed matched, so if that's 0, that means, this term goes away right here, and that means this goes away. So that means the only thing we have to do is get V2 minus here. V2 minus is going to be equal to S21, which is 3/4 times e to the J60. And it's going to be, what's it, minus 2/3 times 0.05 squared e to the J120 degrees, V1 plus. So if you can do me a favor, tell me what this is right here. I can't. That's 0.05 squared, so it's 3/4 e to the J60 minus 2/3 times 0.05 squared e to the J120. And a number I see off the top of my head. Y'all, I mean, the thing was that the V2 plus is 0, because I'm assuming it's matched. That's the whole basis for getting rid of that. What do you get for this? Wow, this is starting to look weird. Is that what, if you look at his solutions, is that what he does?
I think so.
Because that's a lot of manipulation. I mean, the V2 plus equals 0 is the key. But what do you get for that? No. I can't squint and look at it and make it work.
I think
That second number is very small. It's about 3/4 to the J60.
that's what the solution is.
Why?
I think this is what the solutions come up with for V2 minus over V1 plus. I think when you take that.
This is it. This is
Yeah.
going to be V1. This will be it right here, and that will be the actual S. I mean, that will be the forward gain, but then you have to, if you want insertion loss, you have to take minus 20 times the log of that. If you just take minus 20 times the log of 3/4, tell me what you get. I bet you that's real close. Anybody do that? 2 point, what?
Solution is
What?
2.5.
And what's the solution?
2.7.
All right, that's because of this stuff. And, but that's how you get that. It's kind of a pain. Let me do something, now, I wanted to finish 2 things today, and this is not gonna take long. I wanna go through, a simple divider. This is a 3/4 network, but here we're not circulating anything, we're dividing the signal out, and it's the most common thing that you run into when it comes to cabling. And you probably have actually done this in your house, where you went and bought a splitter or you ordered a splitter where it takes, so you could stick one end of a coax cable in it and get 2 out. Now, when you do that, you automatically lose power. But depending on the type of splitter, it has to do with how much power you're gonna lose. Here's a standard, this is a standard, I call it a splitter, it's a divider in the book. Divider, and this is just a 2-port, or 3-port divider. 3-port divider. So it looks like this, and this is in your book, characteristic impedance of Z0. And then they want to split that into 2, where this is going to have a Z0 and this has Z0. So they want to take this incoming signal on port 1, and they want to split it here. The way they do it is this. Be careful that you watch this. They're going to say that I'm going to come in here and I'm going to have something that has Z0 over 3. That's going to be just the resistance. Then I'm going to have another Z0 over 3 that connects to this one. And I'll have another Z0 over 3 connects to that one. And then this is just going to be the center leg of this thing, so that you can see how it connects. Really, your network is simply 3 Z0 over 3 impedances. It's just it's basically a triangle like that. So Z0 over 3 is attached to each of these transmission lines, and all these Z0s over 3 are attached to a central point. Now, here's the important thing when you look at this. Remember, this is assumed it's going into a matched condition. So over here, I have Z0, and when I have Z0 over 3, what I really have is something that looks like a 4/3 Z0. Do y'all follow me? Right here, just look at this upper leg. By the same token, you have another one. You're going to have another 4/3 Z0 here, and I call that grounded. I'll ground this. And now when I look from here to here at the impedance, you see that those two are parallel. Please try to appreciate this. Do y'all see that, class? If you've got Z0 over 3, Z0 over 3, both tied to these transmission lines, and they are in parallel, then you'd have 4/3 Z0 and 4/3 Z0. That means the input impedance for this would be what? Just 2/3 Z0. Do y'all follow me? Because they're in parallel. 4/3 in parallel with 4/3 is 2/3 Z0. Correct, class? Now you're at this point, the center point. And what are you adding to it? This whole thing's just 2/3 Z0, so you have 2/3 Z0 here as the equivalent of all that, and that goes in and feeds Z0 over 3. And that automatically tells me that my input impedance right here is Z0. You all see that, class? Right? And if it is Z0, then what do you know? It's matched, because there's no reflection. Now what's the real problem with this one? There's one obvious problem. You should be able to see it in the heartbeat. They're made of resistors, which means they lose power, and they lose a lot. Yeah, so now we're going to get the S parameters on this one. And it's not hard, but I think you have to appreciate what's going on here. The signal's coming in this way, and some of that signal is going that way, some of it that way. The same exact amount, but you start by saying, well, how much of the voltage is going to be developed here, right at the central leg? Just take a look at that for a second. We have what? Here's the port. I have Z0 over 3 here. And then I have 2/3 Z0 here, right? Correct? Everybody with me? So the signal that gets in here, now remember it's matched, so all of V1 gets in there. When I have V1 here, the value I have here is what? It's going to be V1 times 2/3 Z0 over 2/3 plus 1/3 Z0, or just over Z0, or it's just 2/3 V1 is developed at the center. Do y'all follow me in that, class? Now keep watching. That's how much voltage is developed right here. But I need the voltage developed here, or I need the voltage developed here. I've got the voltage, what I'm really trying to say is if I have the voltage developed here, how much voltage is going to be developed here? Now just think about that. they're in parallel, aren't they? So if I know this voltage here, and I want this voltage, it would be this voltage times Z naught over Z naught plus Z naught over 3. You all follow me? I want you to make sure you see this. Alright, so I have a voltage of 2/3 V1, and then I have a connection through here of Z naught over 3, and I want to know how much voltage is developed here, and that is Z naught, right? So this voltage developed, this voltage developed here will be equal to 2/3 V1 times this impedance Z naught over the sum of the two, or over 4/3 Z naught. And that means it's 1/2. You all follow me on that? I'm just trying to show you how the voltage division works, right? So that means if I look at V2 minus over V1 plus, it would be 1/2. That's a 4 again. V1 or V2 or V3 minus over V1 would be 1/2. Your S parameter matrix will look like 0. All the reflection coefficients are 0. Then 2,1 will be 1/2. And 3,1 is 1/2. Over here, I know I'm out of time, I'm trying to get this in. What I really need to tell you is if you look in your book, this is shown on page 570 and 571. What I'm trying to show you is the first one, 1043. I didn't get to show you how the return losses, how those things are, how the S13 is figured out and S2 or S12 is figured out, but I will on Friday, and I'll go through the Wilkinson's divider and four-port networks. For the quiz Friday, it'll be on S parameters on the stuff that we've done the last 2 lectures, okay? All right, see you then. Sorry I didn't get through this whole thing, but I wanted to do the crazy part.